Now we're going to talk about control hazards. So where do control hazard fit in? Well, we have three different types of hazards we can have. We have data hazards, control hazards, and structural hazards. Data hazards are where an instruction depends on data that's not ready yet. So these data dependencies occur through the register file, and we've seen how we deal with this, with either putting in stalls or with forwarding. Control hazards occur when the choice of the next instruction depends on results that aren't ready. So this is what we're going to talk about now, but it means you may execute the wrong instruction when you have a branch because you don't have the value for the branch yet. And structural hazards occur when the hardware can't support a combination of instructions. So we saw this with the register file, where we were trying to read and write at the same time. If the hardware doesn't support that, it's very hard to make the instructions work. So let's take a look at control hazards that we have with branches. So here we've got some code. There's a branch at instruction 44, and if there is the branch, we're going to jump down to the bottom part. So if the branch is taken, we'll do instructions 40, 44, and then we'll go down to 72 and 76. And if the branch is not taken, we're going to go right through the code all the way to the bottom. So when you look at this code, it makes perfect sense what's going to happen. But now we need to see what happens when you execute this code in a pipeline. So question, in which stage do we determine if the branch is taken? Well, we determine this in the memory stage. The comparison of the two registers is done in the execute stage, but we don't use the result until the next stage. So let's take a look at this and its implications. Here's our pipeline. So when the branch gets over here to the memory stage, that's when we're going to use the results to make the decision. So that's when we send the results over here and we say our next PC is going to be 72 if we're taking the branch. But when we do this, what instructions are already in the pipeline? What instructions are in the execute stage and the instruction decode and instruction fetch stage by the time the branch instruction gets to the memory stage? Well, they're the instructions that came before it, after it, 48, 52, and 56. These ones were already put into the pipeline and have already started executing. So we've started executing these instructions before we decide if we want to take the branch, and they may be the wrong instructions. So if we do decide to take the branch, we should have executed instructions 72 and 76 after the branch, not 48, 52, and 56. So let's take a look at that branch hazard. Here's our program with our branch, and it's at this point that we determine if we're going to do the branch. And if you look what happens before that point, we go ahead and start executing 3 more instructions. And which instructions are these? Well, we just do the standard PC plus 4 and go on to the next instructions. It's only at this point that we can forward the data if we want and figure out which instruction we're going to do. So after clock cycle 4, that's when we update the PC and we figure out which instruction to go on to. So in this pipeline, it takes 3 cycles to resolve the branch, 3 cycles before we know the correct next PC, and in those 3 cycles, we're going to go ahead and execute 3 instructions. And these 3 instructions are only correct if the branch is not taken. If the branch is taken, then we've just executed 3 instructions that are wrong, and that's incorrect execution of our program. So what can we do about this? Can we just stall? Well, we could just stall, but we're going to have an awful lot of bubbles in our pipeline if we do. We'd have to stall for 3 instructions every time we have a branch. That's going to very much hurt our performance. Branches. So can we improve this by changing our pipeline or adding hardware? Well, let's take a look. So here's our pipeline, and the problem we have now is that it's in this stage that we're deciding that we should take our branch. This gives us a 3-cycle delay. If we could move this decision over to the execute stage, we'd only have a 2-cycle delay. And maybe we could do even better. If we could move the branch decision to the instruction decode stage, we'd only have a 1-cycle delay. But if we do this, we're going to have to complicate things. So we're going to need extra hardware here. If we're deciding the branch in the instruction decode stage, we can't use the ALUs in the execute stage. So we'll have to put more logic into the instruction decode stage. So a question, if we could move it even further, that would be better. So could we move the branch logic into the instruction fetch stage instead? Well, the answer is no, and the reason is we need the register values to determine if we take a branch. The register values are only known in the instruction decode stage, so that's the earliest we could go ahead and make this decision. Now, given that, I'll point out that in the next lecture, we're going to talk about ways to predict the decision, so you can make it even before you know what the registers are. So let's talk about how we move this branch computation earlier. So currently we have it all the way over here in the memory stage, and we have a 3-cycle delay. We could move it to the execute stage and have a 2-cycle delay, but we're going to be really aggressive, and we're going to try and move it to the instruction decode stage to have just a 1-cycle delay. So what do we need to do this? Well, the first thing we need is an extra adder to calculate the PC plus immediate. So we can put in the adder there, take our immediate value, and take our next PC value, and then we can send that back to the mux that decides if we're doing the branch. Then we need a comparator to check if the two register files are equal. So we can put in a comparator, and we can connect it up to the register file, and this comparator is then going to control which branch we take, if we go on the standard PC plus 4, or if we go on the branch that's determined by the branch instruction. So let's take a look at what we have now with branches with this earlier branch prediction logic, this branch detection computation logic. So now we're going to go ahead and we're going to determine the branch in the second clock cycle, which allows us to have the correct PC only 1 cycle after we expect it. So now it takes 1 cycle to resolve the branch. So we have 1 cycle in between a branch and when we can go on to the correct next PC. So we've still got this slot in here, which we're going to go through even if we don't take the branch. So this instruction is always executed, and it's called the branch delay slot. So if you can put useful work in here, then that's great. You can do something useful. If you can't, then this is just going to be a wasted slot and you have to put a no-op in it. So now we've got a branch delay slot. And we've now gotten it all the way down to a 1-cycle delay for branches instead of the 3-cycle delay we started with. This is really good. It saves us a lot of performance. In the MIPS architecture, this is exposed to the compiler. So the instruction after a branch always executes regardless of the branch. This breaks the ISA's promise of serial execution. The serial execution says if you have a branch, you only go one way on the branch. What this says is regardless of whether you take the branch, you're always going to execute the next instruction. So this complicates things. What this means from a practical point of view is that the compiler needs to find useful work to put in the branch delay slot. It needs to find other instructions that it can move there so that it has work to do.